So one question people had was still on the three types of carbon NMR. There was the carbon NMR, that's the plain decoupled NMR, and then there was DEP, and then there was DEPT 90, and then DEPT 135. So I'm going to make up a molecule, and I'm going to predict the NMR, the carbon NMR on this molecule. Actually, I want to do this. So I'm just making up a molecule. Okay. I'm going to predict the carbon NMR. Okay, so this is my shift. So I'm going to label this molecule, and then I'm going to go over the DEPT by actually using yeah, let's do this. I can come up with something else if you need me to. So there's this methyl. There's no other methyls on the molecule, so it would have its own signal. Remember, it's an alkyl, so it should show up somewhere between 0 and 100. Then you have this methylene group, which is also an alkyl, but it's between the methyl and the ring, so it's basically an alkyl that's attached to a pi bond, so it should be more downfield. Then you have your ring, which is in the aromatic region. So like we said, both of these are between the 0 and 100, but so this would be somewhere between 0 and 50. This should be somewhere between 50 and 100. And then the aromatics, there is this peak. That's C, that carbon would be C. There's no other carbon attached to an ethyl group, so it's itself. But these two are identical. They're seeing the same environment. So this is D and D. I mean, could you tell one from the other if you rotated the molecule? No. And then E, same thing. And then there's nothing else with a bromine on there. So I see that I have 1, 2, 3, 4, 5, 6 signals. And 2 of them should be in the let me erase this. This shouldn't say 100. Say 150. So 2 of them one of them should be before 50. So I'm just going to put a peak somewhere before 50. And that was our A. And I'm going to put a note here. That was our CH3. And we're going to see how DEPT. If I were just given a spectra, I might not know what I'm looking at, but I could use a DEPT to help me. So here I have the molecule, right? So that's why I could figure this out. But if you didn't have the molecule, you would want to do this. So my other peak, B, would be somewhere in that range. Then we have C. C is attached to alkyl groups. So it's going to be a little bit more downfield, but not really that far. F is attached to the bromine, so it should be pretty far. Okay, and then D and E. E would be a little bit higher because it's closer to the side with the bromine, but not that much higher than D. Okay, so if I didn't have the molecule, how could I have known what some of these peaks were? And DEPT could help us. So let's do DEPT 90. DEPT 90 only tells us CHs, and D is a CH and E is a CH. So the only thing that DEPT 90 would have told us is you would find a peak that matches. And remember, there's numbers here, so let's pretend that this was like 121, 122. I'm just making up those numbers, right? If you look on your DEPT and you saw something at 121 and 122 and they were on there, that means it's a CH. So you know, then that would be an aromatic that has nothing, but the hydrogen on there. So let's talk about DEPT 135. And so 135 can tell us more information. So it can tell us CHs. So remember that our A was a CH3, and CH3s are positive. They show up upright. Our B is a CH2, so it should point downwards. And so CH2s are very easy to know. So if I didn't know that B was a CH2 because I didn't have the structure, I would look at the DEPT 135 and say, "Ooh, that's a CH2," so that helps me. Now, C has no hydrogens on there, and F has no hydrogens on there, so they won't show up at all. But D and E will show up, but they will also be pointing up. So how would I have known that that was a CH versus a CH3? Well, my DEPT 90 only tells me CHs. So if I saw it on both the DEPT 90 and the DEPT 135, then I know it's a CH. But if it doesn't show up on the DEPT 90, then it's a CH3. So it's by deduction.